give you some background on myself and in particular how I came to this subject. So I have been a design build professional for my entire 25-year career so far. And the last 10 years have been at Endeavor Center, which is a sustainable building school. And my interest in carbon accounting came from our general interest at Endeavor in trying to make buildings that kind of hit the highest standards that we can achieve in terms of energy efficiency, in terms of human health, in terms of planetary impact. And, obviously as climate change started becoming, a driving factor in thinking about the environment and human health and all the other elements that it touches on, I got really curious to try to look at the carbon impact of the buildings that we were building at Endeavor. And I started doing my own calculations and then started finding different databases and LCA softwares as they became available, and eventually went back to school back in 2016 to do a master's at Trent University, where I looked at the sort of notion of materials, in particular the materials emissions associated with buildings and the ability to actually have negative emissions to store carbon. And so just finished that MA up last year in 2019. And some of that will come across, some of that research will come across in today's presentation. So the point of this webinar is to give you an opportunity to understand embodied carbon and how it sort of fits into life cycle analysis, to be able to find source data in environmental product declarations, and to understand how you could generate results based on your own building design. And within those results, to understand how biogenic carbon, which is the plant-based carbon in some materials, how that works in terms of storage versus emissions, and to think about those buildings as having net emissions, the emissions from the materials minus the storage potential of the materials, and to look at some of the tools that you can use to do this for yourself. Okay, so to start with, if you're on this call, you probably understand a little bit about climate change, I'm sure. And so I don't want to spend too long here, other than to make clear the point that our industry is, these are generalized numbers, but responsible for almost half of all emissions on the planet. So clearly we're not going to address climate change if we don't address buildings. And a good deal of energy over the last 30 years of all of our collective effort has gone into reducing that building operations percentage there, 28% back in 2017. So, that's a big number. But what we're sort of looking at in the webinar today are the two pieces down in the bottom corner of that graph, the core and shell materials, which is basically your concrete, steel, and glass, which make up about 11% of global emissions, and then kind of all other building materials, which is approximately, it's a hard number to dice out, but about 10%. So you can see that, the material side alone is, 20-odd% of all global human-caused emissions. So in general, we've got to fix this if we want to fix climate change. So the sort of the way in to figuring out how you think about the global warming impact of buildings is through life cycle analysis, and we look at a whole bunch of different phases in life cycle analysis. So as you can see in this illustration, starting from raw material extraction and processing, moving around to manufacturing of materials, transportation of all those materials to a site, the actual construction phase, and then the sort of yellow bar down, or the yellow circle down there, the operational use. That's where most of that energy, or most of our efforts have gone to in terms of reducing the carbon emissions associated with actually operating the buildings. And then sort of you're getting in towards both the maintenance and end of life of materials in those green sections. And so that's a lot to take into account. And it's really important as you go into thinking about this for your own building to sort of say, oh, I'm interested in the carbon footprint of my building. The question is, are you interested in that entire circle of those carbon emissions, or are you interested in a particular phase? And we'll sort of parse that out a bit as we dive in here. Okay. So life cycle assessment is kind of divided up into a bunch of modules. And depending on who's doing the reporting and what the report is intended to convey, some or all of these things might show up in a life cycle assessment. So we'll kind of break up the life cycle assessment into different stages, and we can kind of see then how you would use that to look at particular aspects of your building. And so the first is the product stage, which is A1 through A3. So you can see there that A1 is raw material supply, transportation of raw materials to the factory is A2, and manufacturing itself is A3. And this is what's known as sort of, if you've heard the term cradle to gate, this is what is covered in a cradle to gate analysis. So it's basically really focused on the products, where did the raw materials come from, where did they move to, and what happened to them in the factory to turn them into a building product. So that's the product stage, and that's sort of the easiest stage to find really comprehensive data on because it's very consistent, and the reporting on this is pretty transparent and consistent and comparable. So we do a lot, or in my own work anyway, focusing on the product stage, and it also, short of the operational side, tends to be the biggest piece of a building's total carbon emissions too. So there's a lot to focus on there. The construction stage emissions are also really important, and depending on the kind of construction and where it's happening and what kind of processes are being used, can actually be a surprisingly big piece of the puzzle here. If you're looking at life cycle assessments for products, there tends to be a lot of generalized information used here, and I don't rely on those numbers very much at all because they're sort of saying, well, if my factory is here and we typically ship, in this radius, then we'll put that average, shipping amount and the average shipping method into that assumption and sort of give a general figure. But, obviously depending on where you are, how those materials moved, have they gone, to various warehouses and sub-warehouses on their way to you, and even where you have had to go to get the materials or have them delivered will all factor into that. The use stage emissions is the B category, and I've kind of jumped ahead to B6, which is the use stage emissions. That's your operational energy use. So if any of you are coming from an energy advisor role, or have been focusing your building or design career on making energy efficient buildings, you've sort of been addressing B6. And so obviously that's not something that's attributed to a particular product. So if you are looking at a life cycle assessment for a single product, it's not going to have any figure in B6 because you can't say that, my cellulose insulation used X amount of energy or saved X amount of energy, over the lifespan of the building. You can only say that, the whole building used a certain amount of energy. So that B6 part is kind of its own little slice, and it's a slice that is well addressed in the construction industry already. One thing though that I do want to think about or get you to think about as you think about that part is that in the energy efficiency world, we have been very consumed with the term energy and with energy use as the goal. So reducing the amount of energy a building uses, which is a great thing to do. If you can get the gigajoules or the kilowatt hour usage in the building down, then that's great. But in terms of thinking about the carbon footprint of the building, it's really important to also be adding what the source emissions for that energy are. So, if you can have a building that uses 100 kilowatt hours over a certain time of clean renewable energy, say from a wind tower or a solar farm or something like that, the carbon footprint of that is very different than the same 100 kilowatts of energy coming from a coal-fired electrical plant or from burning natural gas on site or something like that. So when we're thinking about the carbon footprint of buildings, our thoughts about energy efficiency need to sort of adapt to make sure that we're looking not just at the energy as the goal, but as the source emissions times the amount of energy, so that we know what the actual carbon footprint of the operations of that building might be. So also in the B phase is any emissions associated with use, maintenance, repair, and replacement of materials. So for example, if I'm putting asphalt shingles on a roof and my building is going to have, say, a 100-year lifespan, but I need to replace those shingles every 20 years, then there will be 5 more values. The product value will sort of be multiplied by 4 more times in the replacement under B4, because if my building is going to last that long, then I'm going to need to, those shingles are going to need to be manufactured and installed that many times. And same goes with repair. So if the life cycle assessment for products you're looking at has that anything in those columns, they're making assumptions about how long it's intended to last, when repair will happen, how much will be repaired, how much will be replaced. So obviously those are also kind of generalizations and guesses. Sometimes you might have to replace the shingles in 12 years, and sometimes they might last 25. So you have to sort of take the figures from the B section also with a bit of a grain of salt. And then the final, well, not the final, but the final module from the use of the building is end of life. And so here we're looking at what emissions happen from deconstructing the building or demolishing it. So that includes the equipment used to do that, any emissions that are released from the materials as that happens, and then the transporting of those materials and what happens at the sort of waste processing and disposal end of things. So if you throw a bunch of wood into landfill at the end of a building, some of that wood will rot and turn into methane, and there will be emissions associated. So that's all of that stuff is captured at the end of life. And again, you'll see that I keep popping this same quote up as we go, that you must understand the assumptions that are used in this life cycle assessment. So one of my beefs about end of life is really there are only 3 options for end of life in buildings in LCA for the most part. It's landfill, incineration, or recycling. And that doesn't always take into account all the potential options that there are for what could happen at the end of life. And again, a lot of assumptions built in, to how quickly things rot in a landfill, which will vary a lot depending on the kind of landfill, the depth it's buried, the climate that it's buried in, all of those sorts of things. So, just a caution to be, careful of the generalizations built into those numbers. And then finally, it's the D category is implications that are beyond the system boundary. And here's where it sort of includes things like reuse, recovery, and recycling. So if at the end of the lifespan of, say, a steel frame building, you're able to recycle a whole bunch of that steel, that will lessen the emissions required to make new steel. And so, some numbers will show up there to sort of show that there is value, emission offsetting value in a particular material outside of the end of the life of the building. So that's sort of the full life cycle and what's studied in the life cycle when somebody does the life cycle analysis. And so what's really important for sort of you as a practitioner is to be clear on which ones of those impact categories you want to study, know about, and understand for the project you're working on. And also as you're sort of wading into looking at different studies, looking at different comparisons of materials, you have to know in those studies which ones of these elements they were looking at. So if somebody says, oh, the embodied carbon of concrete is better than the carbon footprint of wood, if you were looking at, say, the full life cycle of one of those and only the product stage of another, you're going to get very different numbers. And so it's sort of important that you know both for what you want to learn and share with your clients, but also from what you're reading and hearing about from different products. And manufacturers and associations are really great at kind of picking the LCA results that make their product most favorable. And so, as you're reading those kinds of studies and those kinds of comparisons, you just want to make sure that you're really clear that you know what the study is talking about, so that you'll get a sense of whether or not results are comparable with one another. So some terminology, and the world of this terminology is still really in process. You'll probably be familiar with the term by now, embodied carbon, which I actually think is a terrible term. It doesn't describe what we're talking about very well. But what that means is the embodied carbon is all the emissions associated with a material or a product through its entire life cycle. So obviously a product doesn't have operational carbon. So you can see in this diagram from the World Green Building Council, that little wedge at the bottom for operational carbon, that's not part of embodied carbon, but everything else is. So anything that's attached to the creation of the material, the installation of the material, the repair or replacement of the material, and the end of the life of the material, that full sum is embodied carbon. And now people are talking a lot using the term upfront carbon, which I like. I think it's a good term. It describes all the things that happen, prior to occupation of the building. So it is the upfront portion. But upfront includes all of those A categories. So it includes the material emissions, transportation to site, and construction site emissions. And so once again, if you're looking for comparisons, you need to make sure if somebody's saying, oh, my upfront emissions were X, or the upfront emissions of this approach is X, does upfront include all of those A sectors, or is it including just, one or two or three or four or five of them? That becomes really important. So in my work, I have focused a lot on this product stage, on the A1 through A3. And I do that for a few reasons. One is that this is where the sort of clearest and best data lives. So, as I talked about earlier with all the other modules, there are so many assumptions built into trying to come up with data for all those other models, trying to make averages for transportation, for installation, for how often something is repaired or replaced, or what happens at the end of its life. And it's valuable to think about those things. But at the product stage, it's pretty easy for, and I'll show you how environmental product declarations work, which give really good data on A1 to A3. A certain manufacturer gets a certain amount of material in a certain way, brings it to their factory in a certain way, does a bunch of things to it in the factory, and that's all very measurable. And so the data we get there is pretty robust, and I'll show you how it's sort of third-party verified. And it also, if you look at the full life cycle assessment of a building, this product stage represents a huge chunk of the overall emissions of the building. Sometimes comparable to operational emissions, sometimes more than, sometimes less than, but it's pretty substantial. And so I'm not at all encouraging you to ignore the other categories, but I'm telling you that my focus, and I think there's a lot of value in focusing on that product side, if you want to make really good, accurate studies. And the other reason that I think that the product stage is really important is that our drive to lower emissions for to prevent the worst of climate change from happening has a time window, and what happens at the end of the life of a building is important, but what's going to happen in the next, decade or a couple of decades is really important. And so, acknowledging that the day that building is built, all of those product level emissions will have occurred. So in other words, that carbon footprint is attached to that building because of the emissions associated with those materials from day one. So you can see that on this graph, those sort of goldy yellow bars, they stay consistent because, there was sort of this burst of emissions just to make that building in the first place. And that's going to stay consistent. At some point, if you refurbish or replace things, there will be a little jump. But by and large, that footprint is attached to that building for good. And between now and 2030, so over the next decade, and this depends a lot on the building and how efficient it is and what kind of emissions it has associated with it. But for at least the first decade, it's really common for those material level emissions, those upfront emissions, to outweigh the operational emissions for at least the first decade. Sometimes it can go beyond that. But if we're looking to address climate change, doing the things we can do that will drop emissions now when it's really important to be dropping them is key. And then also to acknowledge that, by 2050, so even 30 years out from now, for a lot of building types, the embodied emissions will be at least half, sometimes more than half, sometimes still less, much more than half of the total carbon footprint of that building. So that's why, my focus is really on this A1 to A3 category. If you are really interested in A4 and 5, so if you really want to get a good picture of that upfront, those upfront emissions, it's really important to do your own study of transportation and installation. The generalizations that are built into LCA softwares, they're pretty rule of thumb. They're pretty based on like, hey, what's the grid average emissions for electricity in a whole country, say. But if you're doing the building in Ontario or Quebec, where there's a pretty clean grid, it's going to be actually really different than, say, if you're building in Alberta or New Brunswick, where there's still a lot of coal power. So, knowing how much energy is used on the construction site is important. What kind of energy and what its source emissions were become really key. Some of my colleagues who live in and build in rural areas have tallied up, just the amount of fuel that they use getting to and from job sites, their whole crew. And sometimes that can have the emissions impact that's the equivalent of all the material impacts for the whole building. So, it's not that I would encourage you to ignore these things, but I would encourage you to study them specifically for your own jobs. And just as a note that that these two categories together, when I've done those studies for our own projects here in Ontario, they've represented about 10% of the A1 to A3 emissions. So not insignificant, but not massively significant either. So if you want to concentrate just on the product scale, on the material scale, I think there's a lot of value to that. And obviously that 10% is partly because I'm here in Ontario with a clean grid. We have a solar powered trailer that actually powers all our job site tools. And so, we're doing a type of construction that is, fairly light in emissions. If you're using a lot of diesel equipment, if you have a lot of commuting that you do, all of those sorts of things, if your closest building supply yard is, a 45-minute drive away and you're doing that every day, obviously those things will make a big impact. Okay, so I'm going to get into a bit of the data now. So everything that we typically use in figuring out what the carbon footprint of a building will be, and especially if you're focusing on the materials side of things, is going to come from environmental product declarations. And an environmental product declaration is a way of expressing the results of a life cycle assessment. It's guided by an ISO standard for life cycle assessment, and it actually looks at 7 different impact categories that those materials will have on the environment. So the global warming potential, which is the carbon numbers that we'll look at when we're thinking about greenhouse gas emissions, is just one piece of data that comes from an EPD. It tends to be the one that people really focus on, but if you are starting to look at EPDs, I would encourage you to, look at the full range, because you'll sort of see that, ozone depletion and acidification and eutrophication and fossil fuel use are all sort of built into there. And if you're trying to sort of refine decisions beyond just their climate change impact, looking at that can get you closer. So in environmental product declaration, we are sort of plucking out the global warming potential numbers that they report on. And the reason I like working with EPDs is that in order for an EPD to be issued, it's at least has to be verified by a third party. And typically it's actually the whole analysis is performed by a third party. And so there are a bunch of program operators in North America. There's also lots in different parts of the world, but the ones on the screen are the main program operators here in North America. And so, you can trust that this isn't company spin on this, on these figures, that somebody has given it a critical eye, has reviewed things, has conducted the assessment themselves in a lot of cases, and so that what you're seeing is a pretty accurate representation of what went into making that product. As you're if you get into looking at EPDs, you'll notice that there are sort of 2 different types of EPDs that are available out there. So some of them are industry-wide EPDs, and that means that, for example, the one we're looking at here on the screen, the American Wood Council and the Canadian Wood Council got together and did an EPD that covers wood products for all of North America. So that means that in the EPD, they took data from a range of different mills, and if you read the EPD, they'll explain their methodology. But so they'll look at the forestry practices, the transportation practices, the milling, the kilning, all of those practices. But what you're seeing as a number is the average of all the mills that they studied, and so that gives us a pretty good general comparison of wood as a material. And then if you were to say look at the industry-wide EPDs for the concrete industry, same kind of thing. And so you can sort of start to see, how does wood stack up versus concrete? What it doesn't tell you is, how does wood from mill A stack up against wood from mill B? And there could be very large differences in there. Sometimes when there exists both an industry-wide EPD and a manufacturer-specific one, or multiple manufacturer-specific ones, you'll see, sometimes a single product in the same category could be 10, 20, 30% better or worse than that average. So, it's not guaranteeing that you're working with the number for the product you're using for your building, but it's a really great way to, find out what product categories you want to be picking from. And then obviously the manufacturer-specific ones, that's where one manufacturer's operation is being studied. And so there you can start to compare. In Canada, there's 2 different companies, CLT companies, that have their own environmental product declarations. So you can see, what the differences between their practices are, and decide if you would prefer to buy from one or the other. So some key information to look at on EPDs. There's a validity period of 5 years from when it's first issued. So you can see the one I'm showing you is actually out of date. And there are, as you're looking around, you will find quite a few out of date EPDs. There was a burst of interest about 10 years ago in producing these, but not everybody has followed through with, redoing them and maintaining them. And it'll also tell you who the verifier was. So, you know, if it's a widely recognized and reputable company, you know, then you have a pretty good sense that the data you're looking at is going to be good. So once you start looking through the EPD, they can be a little bit intimidating. Like, they're quite often anywhere from 10 to 40 pages long. There's a lot of sort of talk about the methodology and where the source data comes from. You're welcome to read it. I've read quite a few. They start to get repetitive after a while because they're basically, you know, outlining a very similar methodology. But key things that you want to look for if you want to work from data from an EPD for your own project. Obviously, it gives a product description, and it is important to note that, you know, one of the problems, it's not a problem, but one of the issues with EPDs and that you know, especially manufacturers will sort of warn you about is the numbers they give aren't necessarily directly comparable to another EPD. So if we're looking at one here for cross-laminated timber, and we're thinking, well, I want to compare a CLT building with a concrete building. Just the number that I see on the EPD is not going to give me that answer, because it's going to be giving me an answer for a certain amount of each material, but the amounts aren't necessarily comparable. So, you know, I will use a different number of either cubic meters of wood CLT or kilograms of CLT to make the same building compared to a certain cubic meters of concrete or a weight of concrete. And so if I'm looking at, you know, a global warming potential figure that's X per cubic meter for wood and X for concrete, a higher or lower number doesn't matter until you know how much of that material you're going to use. And we'll get into that. But so the product description kind of tells you what it's for. Make sure that you know that it's something that's comparable to other things. It will tell you what scopes in the LCA that this EPD addresses. So this is just a cradle to gate. So they're only looking at A1 to A3. You won't find any other data in this report. Sometimes it'll be cradle to grave. You know, each report can be different, but again, you know, that's where you want to know what those terms mean. And you want to, if you're only looking at A1 to A3, then you can be like, okay, I can use this report. Really important is this declared unit. So here they're saying that all the figures they're giving, so all the results in all the categories are for 1 cubic meter of CLT. Now, obviously, you don't build CLTs with 1 cubic meter blocks. So this is where the math that we'll look at later comes in, is you're going to have to figure out how much CLT might go into your building and how to convert that to cubic meters so that you can use this, the data from the EPD. It's going to tell you, you know, what the system boundary is, and we'll look a bit more at that in a second. So here they're looking at extraction through to the final product at the mill gate. So it's a different way of saying they're looking at A1 to A3. Also, there's a bit of a disclaimer here that they're excluding any material or energy flows that are sort of just a small percentage of what goes into the whole system. So, for example, if you have a machine that uses electricity to turn, but every 6 months you have to put a squirt of oil in the bearings, they're probably not counting the oil, but they're counting the electricity. So, you know, they're kind of making a cutoff threshold of how granular the data will get. And here is just that same notion shown visually, and you'll find this in most EPDs, and that little dotted box is sort of showing you that this is what they're accounting for in this EPD. And so this is what the results page of an EPD will typically look like. So it's going to give you those different categories. And like I said, we're looking at the global warming potential. It's expressed in kilograms of carbon dioxide equivalent. And so 1 cubic meter of CLT from this company has 89.8 kilograms of emissions associated with it. So like I said, that's just a raw number. That it doesn't start to mean anything until we until we convert it. But there's the piece that you're going to try to find if you're looking at an EPD. And just so we are clear on how that answer is being expressed, kilograms of carbon dioxide equivalent is how that global warming potential figure is usually represented. And CO2e means that all the emissions that have happened in that product, in the generation of that product, are being normalized to a volume of CO2. And so what that means is if a bunch of methane was emitted, methane is 34 times more potent a greenhouse gas than carbon dioxide. So 1 kilogram of methane would translate to 34 kilograms of CO2e. And same, you can see nitrous oxide is 298 times. So if there was a mix of emissions associated with that product, it's all being wrapped into an equivalent, carbon dioxide equivalent, so that we can compare them. You know, so if you have a material that only emits 1 kilogram of methane, and methane was the way they gave you the answer, you'd have to know that math to compare it to something that only, you know, emits 1 kilogram of CO2. So it's been normalized to CO2e. So anytime you see that E, that's what it's referring to. So then if you're sort of wanting to do your own building level calculations from source data yourself, essentially what you're doing is performing a material takeoff. So whether you do that manually or whether your design program spits that out for you, we'll kind of go through the steps here. So if I have 100 square meters of CLT floor in a project, and it's at 3.5 inches or 0.0889 meters in thickness, then I have 8.89 cubic meters of CLT in that building. So what I want to do is get to convert the amount in my building to the number that I find in the EPD. So in this case, I don't have to do any conversions, but say the EPD had given me the CLT emissions in terms of kilograms of CLT, then I'd have to take my cubic meters, multiply it by the weight of the wood in order to do that. And EPDs can be expressed in a bunch of different ways. So, you know, sometimes there are several conversion steps to get to the answer in the same as the EPD's functional unit. And then I'm going to take that material quantity and multiply it by that GWP factor that I found in the EPD. So I've got my 8.89 cubic meters of material, and it was 89.8 kilograms of CO2e emissions per cubic meter. So that 100 meters of square meters of floor, CLT floor in that building would have just shy of 800 kilograms of emissions associated with it. So that's the cycle that you would go through for one material, and you just sort of repeat that material by material if you're doing your own calculations. And then this is where things, if you're interested in the sort of biogenic materials and the carbon storage potential in those materials, some EPDs will actually give you that information. So we're back with this cross-laminated timber one. And you can see here that they've told us that that cubic meter of wood absorbed 764 point whatever kilograms of CO2 in its lifespan. So that's, you know, the carbon that's in the wood that makes up the body of the wood. There's 764 kilograms of that in the wood. And then we're going to add the emissions. So if you total those three up, that's that 89 point whatever that were the global warming potential of the manufacturing of the wood. And so what you end up with is actually a net storage, the carbon stored in the material minus the emissions during the production of the material, in this case, would actually give a negative number. So if I was using 8 or 9 cubic meters of that wood, I would do 8 or 9 times that minus 678, and that would give me my sort of net storage for that material. A lot of EPDs don't give you that biogenic carbon piece. You sort of have to calculate it out yourself. So here I've taken a snapshot from a cellulose insulation EPD. And the one thing that EPDs always do give you is a composition of the material. So, here you can see they're telling us how much of cellulose insulation is the fire retardants, the boric acid and the ammonium sulfate, and how much is recycled paper products, how much is cardboard, and how much is fiber residuals, sweepings from factories, and how much is water. And so, I can sort of take from here that 86% of the mass of cellulose insulation is biogenic. And then I'm going to determine again how much of that material is in the building. And that comes from the EPD tells me that, dense packed cellulose is packed in at 56 kilograms per cubic meters. And in this case, I'm assuming my building is using 50 cubic meters of that material. So there's 2,800 kilograms of cellulose. 86% of that weight is biogenic. So we saw where we found that. So there's where we apply that number. Half of the weight of that biogenic material is carbon. So for wood, soft woods are 50%. That's the number that gets used, carbon by weight. So of the biogenic material, 50% of that is carbon. So there I've converted it to, I now know how much carbon is in that wood. And then I have to convert that carbon to CO2. So that's a factor of 3.67. And essentially what you're doing there is adding the weight of the oxygen atoms that are going to attach themselves to the carbon atoms when that carbon goes to the atmosphere. So a lot of people get confused. How can the CO2 storage of the material, in this case 4,400 kilograms, be more than the weight of the material itself, which is 2,800 kilograms? So I put 2,800 kilograms of cellulose in my building, and I'm saying that I have 4,400 kilograms of CO2 storage. And that's because when that carbon breaks down and goes back to the atmosphere, whether that's through burning, rotting, however that paper is going to break down, it's going to break down by turning into CO2. And since CO2 is what we're measuring on the emission side, we're sort of converting it so they're comparable. If you're looking for how to find the amount of carbon in various biogenic materials, I use this Phyllis database. They have plant materials, a huge database of plant materials. So in this case, if I was looking for wheat straw, I would find their wheat and rye. So this is one sample of 490 different samples. And down here, it's going to tell me that this particular sample is 47 point whatever % carbon. That will vary. So what I've done in my own work is go, look at 20 or 30 samples from this database and take an average of all of them to come up with that factor. So that's, we've gone through one material calculation. Now, if you're going to do a whole building, you're essentially just going to repeat that. You're going to take all of your material quantities and get them into either volume or mass or both. Then you're going to find EPD data. So maybe you can find the specific EPD for the product you actually are using. Maybe there's a generic industry-wide one that covers that product type, or maybe you find a whole bunch of them and you sort of average them to get an answer. But you can see here on the screen, if you look at each of the different ones, the EPD1 data, some of it's in kilograms per meter cubed, some of it's in kilograms per meter squared at R 5.68. It varies kilogram per kilogram. Sometimes it's done in. So this is where you have to be sure that you're doing your conversions appropriately. But finally, you'll get these totals. So for these two wall systems, wood frame with fiberglass and XPS on the outside, and wood framing and cellulose with fiberboard on the outside. And you'll see here that the R factors of the walls are different. So these two wouldn't be directly comparable. I just clipped these out, but I also compared an R40 wood frame and cellulose. So you get the totals for each material. If there's biogenic carbon content, which there is in the cellulose and the wood fiber board, you would calculate that. You would convert that to CO2, and then you'd get a component subtotal, and then you would end up getting a, you'd be able to add those together to get assembly totals. So you can see that the carbon footprint of our wood frame, fiberglass, and XPS wall is about 5 tons, and our wood frame and cellulose wall is actually storing a little over a ton. So a huge difference, and that's why it's so interesting to look at these numbers, because you can get vastly different totals from different assemblies. All right, see how we're doing for time. Good, okay, everything's going well. So this kind of now expands out to some building scale calculations. So this is now me comparing the same building. So, doing the material takeoffs for these assemblies that you see here. A high carbon concrete and XPS insulation, frame walls, etc. You can sort of look at all of those things. But the building that I was looking at, which is a 4-story, 8-unit multi-residential building, in this form had 212 tons of carbon associated with it. But if I used a different set of materials, you can see there's a blue arrow. I swapped out a bunch of materials there and ended up with a model of the same building that had 68 tons. And then I also swapped out materials again, and I was able to come up with a model that actually had net storage of 15 tons. So this is the same size and shape of building with all the same performance characteristics, the same R values. It can have this wildly different carbon footprint. And that's why I'm so interested in these materials or this approach to looking at materials, because a building that starts its life with 200 tons of emissions already, even if it's a really energy efficient building, that's going to be its predominant carbon footprint on the planet for the next 20, 30 years. Even if it's really energy efficient, the other 2 versions of that building, the one with 68 tons or the one storing 15 tons, using the same amount of energy, they are always going to have a smaller carbon footprint than that building. And that's why, I'm really excited about, using this as a lens to figure out how best to build buildings. And so, as we saw earlier when we just went through the biogenic carbon, those negative numbers are what's coming from those carbon storing materials. So you can see them there in green, some FSC wood on the ceiling, some FSC hardwood on the floor, some cellulose and wood fiber insulation. Those types of materials are what are giving those negative numbers. The building still had some positive numbers too from, it still had a concrete foundation, it used some EPS foam, it used some drywall and windows and stuff like that, but the net emissions ended up being negative. And so once I've done a whole building, what I like to do is convert the total carbon footprint to emissions per square meter. And that makes it easier to kind of compare across different buildings. So, my 4-story MERB in its most intense form had 241 kilograms of emissions per square meter. My best model stored 137 kilograms per square meter. But now, if I want to compare that to another building that I'm doing, if I convert that one to kilograms per square meter, I get to a number where I can sort of see, if this building compares to that building, whereas just having a total emissions, obviously a 10-story building is always going to have more emissions than a 1-story building, but it may per square meter actually be a better building, have a lower carbon footprint. And this is where I would sort of, this analogy I think holds up relatively well, that if you're thinking about these numbers, they are based on really sound and well-verified data, but I would also say, think of them like fuel mileage. Like, that red building is a V8 engine, and, you could build a slightly better V8 engine and it won't use quite as much fuel. But if you have a V8 engine, it's always going to consume more fuel than, say, the 4-cylinder engine or the 6 that might be that blue building. And then, that's really different than, say, an electric engine which is maybe that green type of building. But there are factors that make you can basically drive an 8-cylinder engine gently, and the number will be slightly better. But I think that's not a bad way to think about these numbers. It's not like 100% accurate. If I buy a car that says it's going to get 30 miles to the gallon, I don't flip out if it's actually 31 or 28. I expect that that's the case depending on how I'm driving, where I'm driving, all that kind of stuff. But I know that that's the right range. And I think, we can treat these numbers like that. Like, I'm in the right range. My -11 might actually be -15, and it might be -5. But it's, that's still an order of magnitude different than the 240, which might be 250, or it might be 230. But I'm still, getting a really good sense of how materials are contributing to the emission profile. So if you don't want to do your own calculations from source, which are interesting to do, and it's good to sort of know the methodology, which is why I bothered to go through it with you. But there are some tools that I'm going to show you that make this easier. The first of which is one that we've just come up with at Builders for Climate Action, and it should be on our website this summer, hoping by July 1st. And it, in its spreadsheet version, sort of looks like this, where you put in the area of your building, all your key building dimensions, and then you go through, there's different tabs. So the foundation tab, you will select, say you're going to use a high SCM concrete instead of a regular concrete. You put your tick bar there, and it brings that answer back to the main sheet. But what I like about our calculator is that as soon as you do put in your dimensions, it populates this sheet. So I can scan this list of different ways I can build a foundation wall, and right away I can sort of see, where the materials that are, better or worse than others might lie, and do some comparing right there. And the sheet goes down. It has, the exterior insulation. It's got categories for if you're going to frame and insulate to the inside, but you would sort of tick the boxes in every category that applies. And I'll just go back, and you'll see, you'll sort of get a subtotal. So my foundation subtotal for this particular building was 1,800 kilograms. And these, as you start to populate that, they'll come up and populate this grand total. And it will also give you a kilograms per meter squared by using the floor areas that you've defined here as your overall floor area. So we're really excited to get that one online. It's really been designed for, sort of smaller builders, people who don't want to invest in major LCA software and get themselves trained in it. If you're just wanting to know your material emissions footprint, this is going to be a really great way to do that. There's also the EC3 tool, which is free and available online. And it's relatively new. It just came on at the end of 2019. So right now, their list of materials that you can compare is not, far from complete, and it's definitely stacked towards the world of larger buildings. So you'll see if you scroll through their insulation, there are things that you might regularly use, say, in a residential scale building that aren't here. And definitely a lot of the key building categories for low rise aren't incorporated here yet, but they're working on sort of building that up. The beauty of their site is that this is very much for comparing between materials in the same category. So over here they're going to tell you that where the range of everything in the product category that you've selected is. So I've selected insulating material. So, the range is quite big. And if I select a particular material, it will sort of show me where it fits within that baseline. It will also show me the figures for everything in that category, and you can rate them in different ways. So you can rank them by lowest carbon footprint to highest, or by different type of board insulation, or by manufacturer. And then you can click, and you can actually get to the EPD itself if you want to see the source data. But it also gives you the average for the whole category you're looking at, what's achievable, what a conservative estimate might be and how many samples are in the database. And then once you click on a certain material, it will bring you a more detailed look. So here I'm comparing wood fiberboard insulation to an XPS foam insulation, and you can see that this material was actually the lowest thing on their list, and the XPS was above the 80th percentile, so it's one of the higher materials on the list. So lots of great data there, just maybe not as complete, and it's not going to do the calculations for you. You're still going to have to do your material takeoffs and then apply these numbers to them. The ICE database from England is an Excel sheet that essentially just lists materials and gives you a CO2e figure per kilogram for those materials. So that it's always in ICE given as kilograms of CO2e per kilogram. And so then your job is to, convert out all of your material takeoffs to kilograms so you can do the comparison. What's great about the ICE database is how comprehensive it is, how many materials are in here. It's really complete. It is British, so in some cases, figures can be a bit misleading because our energy sources and some of our raw material acquisitions are different in North America, obviously, than in England. So for example, their figures for timber are really different than North American figures because they don't have any timber. So, they're looking at timber coming from, Northern Europe or Russia with a lot of transportation involved. So, you want to sort of treat that with a grain of salt, but it's a really great comparative and free database. The Athena suite of tools can be really good too. They have an eco calculator for residential assemblies. So they've sort of pre-built a lot of standard residential assemblies here, and you can sort of same as with the Builders for Climate Action one, put your building dimensions in and get some pretty great feedback from Athena. And then there are LCA software packages that you need to buy. Tally integrates with Revit. One-click LCA integrates with a bunch of different design softwares. So the nice thing with those is if you're building your buildings in those software programs, the material quantities will sort of export automatically, and so you don't have to do any of the math. One of the things with these LCA programs, though, is that you're not seeing the sort of source data, which isn't necessarily a terrible thing, but just know that it could be some combination of them using generic numbers, them using EPDs, them using averages of EPDs. It can be you're not always sure what you're getting out, but it's it is really valuable, and the integration with design software can make it really great. So I just to kind of wrap up, I'm really hoping that all of this makes you think that you might want to sort of broaden the way you look at the carbon footprint of a building. So to kind of think about a carbon use intensity that includes the materials and that upfront bunch of emissions with the operational emissions that isn't just an energy efficiency number, but is an actual carbon footprint number based on the kind of energy that's being used at a certain level of efficiency. And that those two things together, if you have a snapshot of what both of those look like, then you have a much clearer sense of what the actual climate change impacts of a particular building will be. And just want to sort of show you a couple of quick case studies here. This is a project that we did at Endeavour with Ryerson University. They had designed a stackable row house. So you can see that illustration in the middle here. The idea was you could put a bunch of these on top of each other and beside each other. And what we did was build, one unit of a potential stackable row house. And we were able to do it with a net storage of 250 kilograms per square meter. So a pretty remarkable amount of storage in a small building. And I like to show this one because you know, clearly this building has a metal roof, it has metal siding. You know, it's not all made out of plant material. A lot of people think that, you know, somehow to do this well and to make a carbon storing building, everything has to be plant-based. But in fact, you know, because it's a net number, you can sort of be mixing materials that have emissions associated with them. So this sat on a Durasol block foundation. It has metal siding. It has a metal roof. It obviously has glass windows and, you know, a number of other emitting materials, but the net storage was quite high. And then going even further, this is an office building that we did for the Teachers Union here in Windsor, Ontario, and it actually has a net storage of 360 kilograms per square meter, and it's a net positive building. So the PV on the roof is actually providing 105% of their annual energy use. So in fact, you know, this building becomes a site of net carbon storage for its entire lifespan. And if we can get all our buildings to that state, then we start to really make a dent in our climate problem. And so at Builders for Climate Action, you know, we're really trying to help builders set goals and targets and sort of move practice along. So, you know, realizing that not everybody is going to be making, you know, massively carbon storing buildings right off the bat. There's a bit of a learning curve and a supply chain curve to get there, but that it's, you know, very easy to stop doing the worst of materials right away and get yourself to a moderate, you know, carbon footprint building, and, you know, start steering the ship towards zero carbon buildings, and then finally carbon storing buildings. So that's the end of the formal part of the presentation. Thanks for sticking with us for that whole time. And if you have questions you'd like me to address, please, by all means, start typing them into the chat box here. And right now, I see one question, which is about studies on the A4 and A5 stages that I can share. Yes, I'm working on that. I sort of did the studies on two of our buildings. One was a site built and one is a prefab. It's not in a particularly shareable form yet, but it's one of the things that I'm hoping to get up onto the Builders for Climate Action website quite soon. So along with the calculator that will live there, the studies that I'm doing on those, and I'm trying to sort of round up other people's studies. Another thing that's sort of missing right now from the upfront carbon world is there's very little data about mechanical, electrical, and plumbing systems and the carbon footprint of them. So, you know, all the numbers I'm showing you here, this is basically in building enclosure and main finishes. So, you know, I'm not including, there's no wiring, there's no plumbing, there's no heating, there's no ductwork, there's no trim, cabinetry, appliances, you know, all of those things. So, you know, by no means is are these figures necessarily the whole building? They're just most of the mass of the materials and the same mass of materials across buildings. And that's why earlier on I was sort of cautioning people to make sure that you're, you know, when you're thinking about comparisons, or when you're doing looking at one study versus another study, you know, knowing what they've included makes it really important. You know, it makes the results really variable. So if I do a whole building, but I'm not looking at, say, the cladding, the flooring, and the windows, and somebody else does a whole building and they have included those, you know, that total could look really different. Okay. Right. I'm seeing both the chat and the Q&A. So, hi, SCM Concrete. Yes, sorry, I try not to throw out acronyms without explaining them, but I think I did that one. So SCM is supplemental cementitious material. So that's things like fly ash, blast furnace slag, silica fume, things that can be put into concrete that aren't virgin Portland cement, but that have the same or contribute to the same binding properties that Portland cement does. So for example, here in Ontario, you can order slag content in your concrete of anywhere from sort of 5 to 45%, and the resulting concrete has the same strength. You haven't sort of changed the engineering properties of it at all, but you've dramatically reduced the carbon footprint because those SCMs are byproducts of other industries. So instead of making Portland cement is one of the highest impact materials that we use in construction, and so by offsetting that with something that is coming from another industry as a byproduct makes a big difference in the carbon footprint. Okay, I see Duncan Patterson, rule of thumb, what are the biggest things we can do as builders to reduce embodied carbon? Use less concrete and use high SCM concrete. That, the concrete tends to be the biggest impact, especially at the residential scale where, the basement is a fair amount of the volume of the material, and it's hard to use non-cement based materials down there. So, the more you can bring a building above grade and the less concrete you can use and the lower the carbon footprint of the concrete, the better. And the other thing you could do would be to transition away from petrochemical based insulation. So, most of the foam based insulations, they have different foams, have very different carbon footprints, but they're all at the high end of the carbon footprint of the insulation world. So for example, if you can sub out dense packed cellulose for spray foam, that's a massive, massive difference that you're going to make with just a single material switch. Did I include the PV array? Yes, I did. But I'm not necessarily thrilled with the data available for the carbon footprint of PVs. I have not been able to find a product-specific EPD from any PV manufacturer. What I found are various, academic LCA studies that are sort of like looking at a process, but not at an actual factory. And the numbers do vary pretty wildly. The numbers I use for my study is in that ICE database from England that I showed you. They look at the three main categories of PV and sort of give a general number for that. And they're sort of looking at European, so I guess that's mostly German, probably PV production. So, if I'm actually getting my PVs from China or elsewhere, it may not be representative. Trends I'm seeing with cost of low embodied carbon materials. Sometimes the low embodied carbon one is the cheapest. Cellulose insulation is basically the cheapest insulation you can get, and it's the best in its category for embodied carbon. You can switch to high SCM concrete with no added cost. Typically the high SCM mixes cost you exactly the same, and that's because the SCMs actually cost the batching plant less than the Portland cement does. So, there are cases like that where those materials either have no cost impact or can be more cost effective. And in some cases, especially things like, wood fiberboard insulation, where right now that's mostly being imported from Europe, that can be higher than cost than, say, putting the same amount of R value worth of foam on the outside of a building. The reason that I like to do a good thorough carbon analysis of a building is that it allows me to figure this out in kind of like a dollars per kilogram of emissions way, and to also balance things out. It's like, okay, if I can, offset some of my carbon footprint with a high SCM concrete, and I can insulate my walls and my roof with cellulose, I've made such a big dent in the overall carbon footprint of the building that maybe it's okay to go with, metal siding, versus a lower carbon siding. So it's, it's always a bit of a, it's just another factor that we put into that game that everybody plays when they're designing buildings of, what products to choose and why to choose them. James asks, with reference to hemp, how could hemp help with overall embodied carbon? Well, I mean, hemp is another plant-based material. It's a material that is, depending where it's grown, sort of like between 40 and 50% carbon by weight. So, you know, when it's used, so our calculator includes both hempcrete and hemp bat insulation. So when that comes out, you know, you'll be able to see directly how those numbers compare. You know, hemp it's no better or worse really than any other plant-based material in terms of its carbon content. So, you know, again, a lot depends on other factors. If you are, say, importing hemp hurd from China or from Europe right now, you would want to make sure that you're, you know, including the impact of all that shipping to get it here. When people build with hempcrete, quite often, well, not quite often, hempcrete is coated in a lime binder, and that lime has a fairly significant carbon footprint. So, you know, all of that has to get factored in. But basically, it's another one of the sort of awesome plant options that can make a building carbon storing instead of carbon emitting. And EPDs for hemp lime or hemp bat. There are 2 European hemp lime companies that have EPDs, and there have also been a lot of LCAs done in the academic world. And so what I do right now is I've averaged all of those together to give me a sort of rule of thumb carbon footprint for hemp lime. And hemp bat insulation, the company that's making it here in Quebec does not have an EPD yet, although they're working on it right now. But again, 2 of the European companies that make essentially the same product have one. So, you know, right now I'm kind of using those European numbers as a stand-in for the Quebec numbers. There's a good chance the Quebec numbers will be even better because their electricity is so clean in Quebec that that'll play a role. But so, you know, right now that's sort of the state of the game in this is that, you know, the data is far from complete. And what I found is I've been able to find some data for every product category that I've been interested in looking at for residential construction, but it's not necessarily the best and most applicable data. So, you know, some of it is coming from Europe, and so it'll be close to what, you know, is actually going on here in North America, but not accurate. Or, you know, it'll be an industry average EPD, but I don't know, you know, if the particular one that I'm buying is you know, on the high or low end of what that industry average would be. So the question about limitations of building size and carbon calculators. So the Builders for Climate Action, it's not that it's only residential, but it's more focused on low rise because the suite of materials that you use is different. You know, when you start getting into multi-story buildings, you're really getting into very specific concrete mixes. You know, every floor assembly, all the structure of a large building uses different types of concrete. You know, in residential, we basically use, you know, 2,500 psi concrete, you know, across the board, and there's not a lot of variation in the mix or the strength, and so, you know, the Builders for Climate Action calculator doesn't need to have a ton of concrete, whereas EC3 I think has like 1,800 different mixes of concrete in theirs, you know, and steel as well. So yes, the calculators could do it all. The problem right now is you know, that who's looking. You know, I know for EC3, they're really their market is, you know, large architecture and engineering firms who don't do residential, and they don't really care, you know, about bat insulations or, you know, things that are a lot more common in residential construction. They're not concerned at all with cladding options. You know, they're not doing as much. There's not as many, you know, types of flooring, say, that you would use in a large building compared to a residence. So some of it is just, you know, who's the audience. Who are you trying to reach, and also how complicated do you want the calculator to be? So, you know, the idea with the Builders for Climate Action one is that most people operating at the low-rise scale they don't have full-time office staff. They don't have people that they're training to use LCA software. You just kind of want a good answer so that you can make a decision and kind of move on. And so, you know, what we wanted to do is make a calculator that was really simple to use. And I would say the difference between us and the Athena calculator, and us and probably every calculator, is that right now the Builders for Climate Action calculator is the only one that's taking carbon storage into account. I think that's really important. I think it, you know, clearly when you start putting negative numbers into an equation, the answers are very different. And I think that, you know, that's an important piece that's missing in a lot of the calculators. And also, you know, because we come from a background of working with more alternative materials, our calculator includes all the conventional ones, but it also includes all the alternatives. And, you know, you clearly don't find things like hempcrete or hemp bad insulation or any of those types of things in Athena or in EC3. So, you know, we're kind of both trying to serve a market, but also influence a market by putting those other options out in front of people. Okay, and from Walter, are you seeing EPDs becoming more common practice? Yes, you know, when I started doing my research and actually trying to gather EPDs for our buildings, that was about 7 years ago. I initially found 6 EPDs, and now my file has about 500, you know, that all relate to sort of residential scale construction. So it is growing, but to your other question, do we need to apply pressure to get their adoption? Absolutely. Like if there's one thing you want to do that would be really impactful after this webinar, it's write to all the manufacturers whose materials you typically buy and ask them for their EPD and tell them that by next year, you're only going to buy products that have EPDs, and sort of lean on them to do that, because, you know, the resolution, the clarity of the kind of answers we're going to get from doing this work are going to be so much clearer the more EPDs there are. And, you know, just to give you an example, looking at fiberglass insulation, fiberglass bat, there's an industry average EPD, and one of the companies, I can't remember off the top of my head which one, went and did a product specific one, and their product specific one has half the carbon footprint of the average. So, you know, clearly they're doing something in their manufacturing process that's way better than everybody else, but we don't have, you know, if every fiberglass manufacturer had their own product specific one, you know, we would be able to say, oh, I'm going to buy from this company because, you know, their product is, you know, far superior to the competition in that way. So yes, you know, the more EPDs we get, the better, you know, answers we're able to get, the better the decisions we're able to make based on that. Are we planning to expand the Builders for Climate Action database? Probably not, because, you know, really you can, that's where the sort of, the existing LCA softwares are really good. You know, by the time you're designing, you know, multi-story buildings, you're probably doing that in a BIM style software, and you're not going to, you know, want to be, you know, putting measurements into our little calculator and getting answers. I think, you know, what we're trying to do is serve a market that isn't particularly well served by the larger LCA softwares. But I think that, you know, if the larger building market is what you're doing, then there probably are, you know, good options out there already. Question from Katie: how much does it cost to get an EPD done? The manufacturers I've talked to, people have paid sort of anywhere from about $10,000 to about $30,000. Depends, you know, sometimes a lot of the data collection is done in-house and is presented to the EPD producer to be verified, or sometimes you sort of pay them to come and, you know, you give them a stack of your utility bills and, you know, all the other information they need, and they kind of wade through it. So I think it has a lot to do with that. So it's not incredibly expensive. And from what I've seen, the process takes, you know, anywhere from a month to about 3 months. I know that the folks at Havelock Wool decided that they needed an EPD about a month ago, and apparently it's going to be out in early May. So, you know, that happened fairly quickly. So it's not a particularly onerous thing. It's one of those things, you know, hopefully it just becomes a standard thing soon, that, you know, you make a product, you do an EPD, and that should be a pretty straightforward thing. And it would be great if, you know, the results of that EPD were stamped right on the package. So the next time I'm, you know, at a building supply center, I don't even have to go find an EPD. I can just look on the package, and, you know, product A has their GWP and product B has their GWP, and I can compare right on the spot. I think that would be a, you know, a great place for things to end up, so that just becomes as much a part of the decision-making process as, you know, the cost and all the other aspects that we weigh in. Okay. I'm not seeing any other questions. So I'd like to thank everybody for taking the time to be with us. I don't know if it's gray and rainy where you are, but it certainly is here. So it's been a great way to spend a bit of time, and I hope that this information has been helpful. And one last question: do you have your data available with all the sources? Yes, if you'd like to look at the study I did for Builders for Climate Action, that thesis is available online. You can find the link to it from Builders for Climate Action, and so that has, you know, everything, all the EPDs, all the math is there. So if you'd like to wade through that, it's not exactly super compelling reading, but it's there's a lot of figures there. And you know, as we work on the calculator, all of that, the calculator will have all of that information visible as well. And I'm seeing another question. The Zero Net Carbon Coalition and Carbon Leadership Forum's calculator, comparing reuse of existing buildings with new build. Yes, I know of that calculator. I think it's really interesting. I think they've set themselves up for a huge challenge because, you know, the reuse in an existing building has many facets to it. So, you know, if you can basically move in and change some interior walls, then there's going to be hardly any carbon footprint. If you're taking an old building and trying to bring it up to current energy standards, and, you know, put a lot into the change of use, and maybe you're changing out mechanical systems, that's going to have a larger carbon footprint. But, you know, I think the track they're on, which is that, you know, the sunk investment in the carbon footprint of a building that's already there is almost always going to be less than the carbon footprint of trying to make that building again. You know, as long as some elements of the structure remain, especially for larger buildings, it's that structure, it's the steel and or concrete and or glass that makes up the vast percentage of the carbon footprint. So if you can keep that old structure and put a bunch of new stuff in and on it, and especially if you can put carbon storing materials in and on it, it's almost always going to work out to be better from the upfront emissions point of view. And then the question is, you know, are you able to make it as efficient as a new building would be? And if not, you know, what's the impact of that? But I think, yeah, the carbon advantages of building reuse are huge, and that the materials that tend to have the highest impact tend to be the ones that we leave in place on an existing building. Oh, okay. So when will the Builders for Climate Action calculator be available? That will be available sometime in the summer. We're sort of shooting for a July deadline. It's being sort of beta tested right now, so it should be available online within a couple of months at the outside. And another question come in. The solar array on the trailer, why is that better than using grid power? It can be, and it doesn't necessarily have to be. Depends on whose grid you're using. You know, in a province like Ontario or Quebec, where there isn't a huge carbon footprint to the electrical grid, it may not be a particular savings. But what it is better than, for sure, is using gas-powered or diesel-powered generators. So, you know, in the low-rise world, we see a lot of people, you know, getting to a bare site and basically, you know, running the entire job site on a gas or diesel generator until the electrical service is brought in and hooked up. And in that case, you know, again, sort of like the driving back and forth to the job, sometimes the emissions from the on-site gas or diesel generator can be the equivalent of the emissions of all the materials that go into the building. So, you know, the solar trailer we use is more an attempt not to avert using grid power, but it's to avert using a generator when there is no power. Okay, and I think we are at the end of our time. Once again, I really want to thank everybody. Those were great questions, and obviously lots of interesting, good thinking going on out there. And I really appreciate you taking the time to tune in and spend the last hour and a half with us here at Endeavour. And hopefully you are, you know, going to start to bring some of this thinking to your practice. And always glad to, you know, hear from people as they start coming up with carbon storing buildings in their practice. Okay, thanks everybody, and enjoy the rest of your day.